A 1,200-ton stone once traveled across a rugged valley. Ancient builders achieved this without machinery, and we are finally learning how. This video reveals the precise engineering experiments that are solving the megalithic transport mystery. You will see how modern science is reconstructing the ingenious methods used to move mountains across impossible terrain. How did a society without wheels orchestrate such a feat? And what does their forgotten toolkit say about human ingenuity? The answers lie not in myth, but in the physics of sledges, levers, and human coordination tested in dirt and water today. What do you think is the most surprising tool our ancestors might have used? These silent stones speak a universal language of ambition. From the windswept plains of England to the volcanic slopes of a remote Pacific island, cultures separated by vast oceans and millennia chose to undertake the same staggering task. They decided to move mountains piece by piece. The iconic circle of Stonehenge, with its massive lintels perched atop uprights, is just one verse in a much longer global poem written in stone. Scattered across the world are similar testaments to determination: the dolmens of Korea, the towering temples of Malta, the mysterious alignments of Karnak in France. Each site is unique in its cultural meaning, yet they all whisper the same tantalizing question: how did people accomplish this? The raw material for these wonders did not simply appear at the building site. The giant bluestones of Stonehenge were quarried over 150 miles away in Wales. The moai of Easter Island were carved from the rock of an inland volcano and then somehow transported miles to the coast. This is the shared thread, the common engineering puzzle that connects these ancient builders across time and space. They all faced the fundamental problem of transportation, of translating a monumental vision across a landscape that offered no easy path. It is a mystery of physics and logistics, a challenge that would give a modern engineer pause, yet one that was solved repeatedly in different corners of the world, long before the invention of the wheel or the engine. This global phenomenon suggests we are not looking at a single lost secret, but rather at a profound understanding of basic principles, a toolkit of ingenuity that was discovered, forgotten, and perhaps rediscovered by human minds confronting the same immense obstacle. That childhood intuition holds the first key. You know the feeling: sliding a heavy box across a polished floor is effortless, but trying the same thing on a thick carpet is a struggle. Our ancestors mastered that simple principle on a monumental scale. The most enduring and widely tested theory for megalithic transport revolves around the sledge and the roller. It is not about brute force, but about cleverly outsmarting friction. Imagine a giant stone block resting on a sturdy wooden sled. Now, place a series of logs underneath that sled, perpendicular to the direction of travel. This transforms the problem. Instead of dragging a massive weight across the ground, you are now rolling it. Each log acts as a temporary moving section of track. As the sled moves forward, rollers from the back are picked up and carried to the front, creating a continuous pathway. It is a beautifully simple cycle of motion. Modern experiments have put this idea to the test with remarkable results. Archaeologist Mark Whitby and his team conducted a famous experiment using a 1-ton concrete block, a replica wooden sledge, and a crew of volunteers. On a prepared track of wooden rails with the addition of a simple lubricant, a team of around 20 people was able to move that massive weight with surprising control. The physics behind it is all about reducing resistance. The rounded surface of a log roller creates far less friction than a flat sled scraping the earth. But the real secret weapon was likely the track itself. A prepared pathway of leveled earth or wooden rails prevented the rollers from sinking into soft ground, which would stop everything. And then there is the lubricant. water, animal fat, or a slick slurry of wet clay applied to the rails would have dramatically reduced the grinding resistance, turning a Herculean pull into a manageable, steady haul. This was not magic, it was practical physics, a system where preparation and ingenuity multiplied human strength. But moving a 1-ton block is one thing. What about stones weighing 50 or 100 tons? The principles scale up, but the logistics become exponentially more complex, demanding not just strength, but impeccable coordination and a deep understanding of the landscape itself. But a sledge requires a clear path forward. What happens when the terrain is uneven, or when a stone needs to be precisely positioned onto a waiting platform? This is where a second principle of ancient engineering shines through: the clever use of leverage. Think of the simple act of prying open a lid with a flat tool. That concentrated force, magnified by the length of your tool, is leverage in its purest form. Experimental archaeologists have taken this everyday concept and scaled it up to move mountains. The key tool is the wooden lever, often paired with a sturdier frame for support. This system transforms a small, coordinated push into a powerful, controlled motion. Instead of dragging a stone, you can literally walk it. Here is how it works. A team places several strong wooden levers under one edge of a massive block. Using smaller stones as fulcrums, they push down in unison. The block rises just a few inches. Before it settles back, another team quickly slides a wooden crib or a flat stone underneath to hold that new height. Then they reset the levers, lift again, and add another crib. Through this patient, rhythmic process, the entire stone is incrementally raised. Once elevated, it can be pivoted or nudged forward with astonishing precision using the same lever technique. Controlled experiments have proven this method's effectiveness. At the Baalbek Museum in France, researchers successfully moved and positioned multi-ton limestone blocks using nothing but wooden levers, logs, and a coordinated team. They demonstrated how a stone could be walked across a field or carefully rotated into its final alignment. This was not brute force, it was mechanical intelligence. It shows a sophisticated understanding of balance, pivot points, and incremental progress. A small group working with rhythm and communication could achieve what a chaotic crowd could not. This leverage system speaks to a deeper truth about these ancient projects. They were exercises in patience and physics as much as they were displays of power. Each slight lift, each tiny shift, was a victory of mind over mass, bringing an impossible vision one deliberate step closer to reality. Lifting and dragging are powerful, but they demand a prepared landscape. What if the landscape itself was the problem? A third, more enigmatic principle flips the script entirely. Instead of moving a stone across the ground, you make the stone move itself. This is the stone rolling hypothesis, a paradoxical idea where you harness a block's own weight and shape to create motion. Inspired by historical accounts from other cultures, experimental archaeologists have tested a fascinating technique. They attach temporary wooden frames, often called rockers or cradles, to the sides of a rectangular stone. These frames transform the flat, stubborn block into something that can be rocked. Picture trying to move a heavy washing machine. You tilt it onto one corner, then the other, walking it forward in a rhythmic, rocking motion. Now scale that idea up to a 20-ton granite slab. With sturdy wooden rockers secured to its sides, a coordinated team using levers could tilt the stone onto one rocker, then let it fall forward onto the other. Each controlled fall translates into a small forward roll. The mechanics are brilliantly efficient. Unlike dragging, which fights constant friction, the rolling method uses the stone's downward momentum during each tilt to assist the movement. The energy input is focused into short, powerful lifts, followed by a recovery phase as the stone settles. Experiments suggest this could be significantly less exhausting over long distances than pure dragging, especially on uneven terrain where a sledge might get stuck. The major question, however, lies in the evidence. While the technique is mechanically sound and demonstrably works in tests, finding proof that ancient builders used it is difficult. The wooden rockers, being temporary attachments, would have been dismantled and reused or simply rotted away, leaving no trace on the stone itself. This absence in the archaeological record makes it a compelling theory born from engineering logic, yet one still waiting for that single, definitive artifact to confirm it was part of our ancestors' real-world toolkit. Yet another principle emerges from the water itself, a liquid highway hiding in plain sight. The idea of floating a 50-ton stone down a river seems almost fantastical, yet water transport represents perhaps the most elegant and energy-efficient solution available to ancient engineers. Moving a megalith by boat or raft transforms an impossible land drag into a manageable, buoyant journey. The physics are profoundly simple. Water supports weight, eliminating the crushing friction of the ground. A stone that would require hundreds of people to drag might be towed by a few dozen in a boat or guided by paddlers on a raft. This isn't just theory, it has been tested. One of the most compelling experiments focused on the blue stones of Stonehenge. Researchers, including archaeologist Mike Pitts, constructed a replica Neolithic log raft. They loaded a multi-ton stone onto it and attempted to navigate the waterways theorized to connect the Welsh quarries to Salisbury Plain. The trials revealed both the promise and the peril of the method. The raft successfully supported the weight, proving the basic concept was sound. The stone floated, but the real challenge lay in the logistics, the unseen engineering of loading and unloading. Getting a multi-ton block from the quarry face onto a waiting vessel without modern cranes required another layer of ingenuity, likely involving earthen ramps, controlled tipping, and careful buoyancy calculations. Once afloat, the journey was not without its own hazards. Currents, tides, and weather would have demanded skilled navigation. The experiment showed that while river travel was plausible for many of the smaller bluestones, coastal routes may have been necessary for longer segments, turning the sea itself into a Neolithic superhighway. Geographic analysis adds strong support, as many major megalithic sites are situated near ancient waterways that have since silted up or changed course. This water theory shifts our perspective entirely. It suggests the builders were not just masters of the land, but savvy readers of the natural world, using its existing pathways to achieve the seemingly impossible. They didn't fight the landscape, they collaborated with it, letting rivers carry the weight so human hands could guide the way. The true test of these methods was not a laboratory floor, but the unpredictable face of the earth itself. A megalith's journey was a marathon across a living, breathing landscape, not a sprint down a smooth track. After leaving the quarry, these colossal stones would have encountered a gauntlet of natural obstacles: dense forests with tangled roots, soft and sucking marshes, steep inclines leading to a building site, and rivers that needed crossing. For experimental archaeologists, this is where the real puzzle begins. To understand the ancient engineer's mind, they must recreate these challenges and see which techniques hold up under pressure. Their test sites become arenas of mud, slope, and water. They dig pits and saturate the earth to simulate a prehistoric wetland, then try to move a weighted sledge across it, observing how quickly rollers sink and become trapped. They construct earthen ramps at precise angles to test the limits of uphill hauling, measuring the point where human power alone is no longer enough and a clever counterweight system might have been required. These are not just demonstrations of strength, they are forensic investigations into failure and adaptation. The most revealing insight from these muddy, hands-on trials is that there was never a single universal solution. The ancient toolkit was flexible by necessity. Imagine a team transporting a massive stone block. On a long, flat stretch of hard-packed earth, they might employ the sledge and roller method, making steady, efficient progress. But then the path reaches a rocky outcrop or a steep embankment. Here, the rollers are useless, so the team switches tactics. They use levers and cribbing to carefully walk the stone up the obstacle, inch by controlled inch. Later, they arrive at the bank of a wide, slow-moving river. Instead of attempting a perilous crossing, they might construct a raft, using the water's buoyancy to carry the load effortlessly for the next leg of the journey. This adaptive intelligence is the true genius behind the monuments. It reveals builders who were master readers of their environment, who understood that the landscape was not just an obstacle to overcome, but a series of tools to be used. Each hill, each stream, each type of soil presented a different equation, and they had the practical knowledge to solve each one, seamlessly blending physics with an intimate familiarity of the land beneath their feet. The physics of sledges and levers tells only half the story. Every successful experiment points to a deeper truth. The real machine was not made of wood, but of people. Modern reenactments provide a startling window into the human scale of these endeavors. When a volunteer team strains to move a 1-ton replica block, researchers are not just testing friction, they are gathering data on sweat, rhythm, and breath. They count the number of hands needed on the ropes, measure the bursts of energy required for each pull, and calculate the staggering caloric cost. The numbers that emerge are humbling. Moving a single medium-sized megalith could require the sustained effort of dozens, sometimes hundreds, of individuals, consuming thousands of calories per person per day. This transforms the mystery from a technical puzzle into a profound social question. How do you feed, organize, and motivate an army of laborers for a project that might span generations? The experiments suggest the work was far from chaotic. Success depends on rhythm. A team pulling a sledge does not simply heave, they must pull in perfect unison, often guided by a leader's chant or drumbeat. This synchronization turns individual effort into a single, powerful pulse of motion. We see this in reenactments, where a disorganized tug of war fails to budge a stone, but a coordinated crew moving as one can make it glide. This level of coordination implies a sophisticated social structure, a hierarchy of foremen, rope teams, and lever crews all acting with shared purpose. It speaks to a society capable of remarkable planning and discipline, where the collective goal superseded individual hardship. This brings us to the most compelling question of all, the why. The engineering reveals the how, but the human cost forces us to confront the motivation. What belief, what shared vision was powerful enough to justify such an immense investment of a community's energy and resources? The stones were likely more than monuments. They were anchors of identity, expressions of cosmology, or sacred contracts with the divine. The very act of building together may have been as important as the finished structure, forging social bonds and reinforcing a collective identity that could withstand the challenges of their era. The true marvel, then, may lie not in the silent stone finally set in place, but in the chorus of voices that sang it there, a testament to what humans can achieve not in spite of their community, but because of it. The strength of a community could move the stone, but it was the strength of their materials that made it possible. Every lever, every sledge, every rope was a critical link in a chain of physics, and if one link failed, the entire endeavor would collapse. This is where experimental archaeology shifts from grand demonstrations to meticulous forensic science, testing not just methods, but the very substances of the Neolithic world. The true boundaries of ancient engineering were drawn by the fibers of a rope and the grain of a tree. Take the humble rope, the literal tie that bound human effort to stone. Modern steel cables can handle tons of force, but what about ropes made from twisted plant fibers or strips of animal hide? Researchers have painstakingly recreated these ancient cords using materials like hemp, flax, and rawhide, then subjected them to stress tests. The results are both impressive and defining. A well-made hemp rope, perhaps as thick as a man's wrist, could withstand a pulling force of several thousand pounds. But this strength came with critical limitations. Such ropes are vulnerable to abrasion, fraying quickly if dragged over rough rock. They also stretch under load, storing energy like a spring, which required teams to pull in smooth, coordinated unison to avoid sudden, dangerous snaps. The experiments reveal that successful transport likely involved not just one massive rope, but many smaller ones, distributing the load and providing redundancy. If one rope failed, others could hold, preventing catastrophe. This material constraint directly influenced the scale of the operations, defining how many people could effectively pull on a single stone before the ropes themselves became the weakest point. Then there is the wood. Not all timber is created equal, and the choice of tree was a foundational engineering decision. For sledges and rollers, you need wood that is strong yet flexible, hard enough to resist crushing but not so brittle it would splinter. Through load testing, researchers have identified species like oak, ash, and elm as ideal candidates for their combination of density and tensile strength. A sledge made from a massive oak beam could distribute the weight of a multi-ton stone, while rollers made from straight-grained ash could endure repeated compression as the stone passed over them. But here, the experiments uncover another layer of ancient ingenuity: the use of green wood. Freshly cut timber, still saturated with sap, is actually more flexible and resistant to splitting than seasoned, dried wood. This suggests that builders may have harvested trees specifically for a project, using the material in its optimal state before it could dry and become brittle. The very landscape was their lumberyard, and their material science was born from intimate knowledge of local forests. Perhaps the most elegant material solution, however, was underfoot. The mystery of the lubricant. Dragging a wooden sledge directly on dirt or even on log rollers creates immense friction, a problem that grows exponentially with weight. The answer, tested in modern experiments, lies in a simple slurry. By mixing water with local clay, a slick plasticine layer can be created on the track. As the sledge moves, this wet clay paste flows under the runners, forming a constantly renewing, low-friction interface. It turns the ground into a temporary, slippery rail. Some experiments have even suggested that certain fatty substances, like animal grease, could be used in combination with this clay mix for an even more effective glide. This isn't a high-tech solution, it is an astute observation of natural physics. The right clay, when wet, becomes a thixotropic fluid, meaning it becomes less viscous under pressure, exactly what a moving sledge provides. The stone essentially floats on a self-replenishing film of mud. This grounding in material reality is what separates plausible theory from pure speculation. It shows that the most advanced technology available was a deep, applied understanding of the environment, where every substance, from a tree trunk to a patch of clay, held a potential function in the grand and practical task of moving mountains. But perhaps the most dramatic test of these ancient principles unfolded on a remote Pacific island, where the evidence is written not in wood, but in the fallen giants themselves. Easter Island's silent moai present a transport puzzle unlike any other. These colossal statues, some weighing over 80 tons, were carved from the rock of an inland volcano and then somehow moved miles across the island's rugged terrain to their coastal platforms. For decades, the accepted theory involved elaborate systems of log sledges and rollers, a massive undertaking requiring vast amounts of timber. But then, a radical new idea emerged, one that seemed to defy common sense. Researchers Terry Hunt and Carl Lipo proposed something astonishing. They suggested the moai were not dragged horizontally, but walked upright to their final resting places. Their theory was born from observation. Many of the statues found abandoned along the ancient roads were not lying flat, as if they had fallen from a sledge. Instead, they were face down with their long, tapered bases pointing forward in the direction of travel. This positioning looked less like a load that had been dropped and more like a figure that had toppled while moving. To test this, Hunt and Lipo worked with a team and a concrete replica moe. They attached ropes to the statue's head and base. Then, with two teams pulling in a careful, rhythmic coordination, they demonstrated how the statue could be rocked side to side, using its own rounded base as a pivot. With each controlled rock, the moe would take a small step forward. In the experiment, a surprisingly small crew was able to walk the multi-ton replica hundreds of meters. The method was mesmerizing to watch, giving the eerie impression that the giant stone figures were indeed marching across the landscape. This walking theory captured the public imagination, offering a seemingly elegant solution that required far less material than building miles of wooden track. It suggested a profound intimacy with the statue's form and balance, turning the moe from a passive burden into an active participant in its own journey. Yet, as with any compelling idea, it sparked immediate and fierce debate. Critics pointed out that the island's actual roads are littered with broken and abandoned moe, which they argue are evidence of transport failures and accidents, not a routine practice. They question whether the method could safely scale up to the largest statues without causing catastrophic damage to the delicate stone features. Competing experimental models have returned to the Sledge hypothesis, but with a local twist. Some researchers propose the use of a specialized wooden sledge called a manga iua, a forked sled described in oral tradition, which could have cradled the statue and been pulled on lubricated tracks of sweet potato paste. This older theory emphasizes the communal effort and resource management of the Rapa Nui people. What Easter Island teaches us is that a single archaeological site can generate multiple, equally plausible engineering stories. The walking theory and the sledge theory are not just competing ideas, they are different lenses on the same problem. One highlights minimalism and kinetic ingenuity, the other emphasizes communal labor and prepared infrastructure. Both are born from the same experimental spirit, the drive to get our hands dirty and test the past. This ongoing debate is not a failure of science, but its greatest strength, showing how our understanding of ancient ingenuity is always evolving, one careful step or one steady pull at a time. But if we seek the absolute pinnacle of megalithic ambition, we must travel to the Bekaa Valley of Lebanon. Here, at the base of the Roman Temple of Jupiter, rests a feat that dwarfs even the grandest Neolithic projects. 3 limestone blocks known as the Trilithon lie perfectly fitted together. Each one is a staggering 800 tons of solid rock quarried over a mile away. This is not the work of a decentralized Neolithic community, but of an empire. The Romans approached the problem with the full might of their military engineering and imperial organization, offering a fascinating contrast to earlier methods. Modern researchers studying Baalbek face a different scale of puzzle. The focus shifts from sledges and levers to the potential of massive wooden cranes, intricate systems of capstans and pulleys, and the most logical solution of all, the monumental earth ramp. Imagine an inclined plane of compacted soil and rubble, rising gradually from the quarry to the temple platform, wide enough for teams of oxen or hundreds of men to haul the stones straight up its slope. Experiments here involve less physical reenactment and more sophisticated computer modeling and small-scale physics. Engineers calculate the angles of incline needed to prevent collapse, the tensile strength of Roman-era ropes for capstans, and the sheer volume of earth required for such a ramp, which would have been an enormous construction project in itself. These calculations reveal the Roman advantage, a command of resources that was almost industrial in scale. They could mobilize legions of laborers, employ skilled military engineers, and harness draft animals on a level earlier societies likely could not. The mystery of the Trilithon, then, is not one of forgotten physics, but of logistics and imperial will. It shows a society applying known principles of mechanics, but at a magnitude made possible by absolute control over manpower and materials. The stones of Baalbek stand as a testament to a different kind of ingenuity, one born from hierarchy, command, and the relentless engine of an empire's ambition. There is a hypothesis that ventures beyond wood and rope into the very air we breathe. Some propose that the ancients mastered a hidden force, using the focused power of sound itself to move their mountains. This is the idea of acoustic levitation, a speculative frontier where chants, drums, or tuned instruments generated vibrations that somehow reduced friction, or in the most extraordinary claims, caused stones to float. While firmly outside mainstream archaeology, this captivating notion has inspired a unique branch of experimental inquiry, one that asks not just how stones were moved, but how sound interacts with the physical world in unexpected ways. Modern researchers have constructed precise vibrating platforms to test a more grounded concept known as acoustic lubrication. In these experiments, a heavy object rests on a bed of fine granules like sand. When the platform vibrates at a specific resonant frequency, something remarkable happens. The particles begin to fluidize, behaving less like a solid and more like a liquid. The object on top suddenly encounters far less resistance and can be moved with a gentle push. This isn't magic, it's a demonstrable physics phenomenon where organized vibration overcomes static friction. It reveals a plausible, if highly specialized, mechanism where rhythmic sound could have made a sledge journey across a sandy patch dramatically easier. The leap from this laboratory effect to floating megaliths, however, is vast. No experiment has shown that sound frequencies can negate gravity for massive, dense stone blocks. Yet, the persistence of this idea in both modern speculation and ancient legends from various cultures serves a valuable purpose. It reminds us that the human drive to explain the unexplained naturally pushes at the boundaries of conventional science. These fringe theories challenge researchers to ask sharper questions and to examine the ancient toolkit for any potential use of resonance we might have overlooked. They highlight a profound truth about these monuments, that their sheer scale continues to inspire awe and wonder, compelling us to explore every possible explanation, from the rigorously practical to the edges of the imaginable. The raw power of the human body was not the only force ancient engineers could command. In many parts of the world, a living engine walked beside them, the domesticated ox. Long before the wheel became common, these patient animals represented a revolutionary source of traction, a biological machine that could multiply the efforts of a work crew many times over. Experimental archaeology has turned to these powerful creatures to test a critical question: could animal power have been the missing link in moving the very largest stones? The answer lies in the mud and strain of modern trials, where researchers harness oxen to weighted sledges to measure their true capacity. The results are telling. A well-trained team of 2 oxen can pull a load of several tons, a force equivalent to dozens of strong adults. This potential changes the logistical equation dramatically, suggesting that for societies with access to cattle, the most monumental tasks may have relied on a partnership between human coordination and animal strength. But this partnership was not as simple as just tying a rope to a horn. The experiments reveal a world of subtle engineering challenges, starting with the harness itself. A poorly designed yoke could choke an animal, drastically reducing its pulling power and causing injury. Researchers have tested various yoke designs against the anatomy of the ox, finding that a padded wooden yoke that rests across the powerful shoulders rather than the neck allows the animal to use its full weight and muscle most effectively. This single innovation, born from observation and trial, could double or triple the useful force an oxen team could provide, yet harnessing the power is only the first step. The experiments also delve into the immense challenge of training. Oxen are not innate beasts of burden. They must be painstakingly taught to pull in unison, to respond to vocal commands, and to remain calm amid the shouting and chaos of a major construction site. This training represents a significant long-term investment for a community, requiring specialized knowledge passed down through generations. It implies the presence of skilled animal handlers, integral members of the engineering team whose expertise was as vital as that of the lever crew or the track builders. Furthermore, the geographical distribution of this technology is a crucial clue. In regions like Western Europe, where cattle were central to the Neolithic economy, the use of oxen for megalith transport is highly plausible. The famous Carnac alignments in France, for instance, sit in a landscape long shaped by pastoral farming. In other parts of the world, however, such as Easter Island or the pre-Columbian Americas, large draft animals were simply not present. This stark limitation reinforces a key insight from all these experiments. There was no one universal secret. The technological toolkit was always a reflection of local resources, a brilliant adaptation to what the environment provided. In some places, the solution was a chorus of human voices and the groan of ropes. In others, it was the deep, steady breath of oxen leaning into their yokes. This partnership between human mind and animal muscle completes the picture, showing that our ancestors' ingenuity lay not in conquering nature, but in weaving themselves more deeply into its fabric, finding powerful allies in the creatures they lived alongside. The tools themselves are a testament to a different kind of patience. To truly walk in the footsteps of a Neolithic engineer, you cannot simply pick up a modern chainsaw and cut a roller. The most revealing experiments go further. They start from scratch, using only the materials and methods that would have been available thousands of years ago. This is the heart of experimental archaeology, a discipline built not on theory, but on the feel of flint in your hand and the ache in your shoulders from a day's work done the ancient way. Researchers begin by quarrying the wood itself, using stone adzes and mauls painstakingly knapped from flint or shaped from copper. Each swing is a lesson in economy and angle, removing wood not in clean, quick slices, but in a slow, controlled process of crushing and splitting the grain. To shape a single massive oak beam for a sledge might take weeks, not hours. The joinery is equally authentic. There are no nails or screws. Instead, wooden pegs are carved, mortise and tenon joints are chiseled, and everything is bound together with ropes made from twisted plant fibers or strips of rawhide. These lashings are not just knots, they are sophisticated tension systems, holding immense weight through clever friction and interlocking loops. Following a team as they build a sledge, this way transforms our understanding of the project's timeline. It was not a sudden burst of activity, but a sustained campaign of preparation. Specialized craftspeople, the woodworkers and rope makers, were as vital as the pullers and lever crews. Their knowledge was a form of living technology, passed down and refined over generations. This painstaking recreation reveals something profound about the society behind the stones. The investment in time and skill speaks to a deep, communal commitment. It suggests that building these monuments was woven into the very fabric of their culture, a cycle of teaching, learning, and doing that turned raw materials into sacred geometry. The final product, that sturdy sledge or that taut rope, was more than a tool. It was a physical manifestation of shared knowledge and purpose, ready to meet the stone. The most efficient path was not always the most direct one. Modern researchers are uncovering a hidden layer of intelligence behind these journeys, a kind of prehistoric logistics that turned raw landscape into a calculated blueprint. Moving a megalith was never a haphazard trek. It was a masterclass in applied mathematics and geometry, planned with a precision we are only now beginning to fully appreciate. Today, experiments have moved beyond physical reenactment into the digital realm, where software becomes a time machine. Using satellite data and digital terrain modeling, archaeologists can now reconstruct the ancient topography with astonishing detail. They feed this digital landscape into algorithms that analyze slope, soil type, and elevation, calculating the path of least resistance from quarry to building site. It is a process of reverse engineering not just the method, but the mind of the planner. These digital models reveal something profound. The routes taken by ancient builders often align almost perfectly with the most energy-efficient path predicted by modern computers. They avoided the steepest inclines, navigated around soft, boggy ground that would swallow rollers, and sought out natural ridges and firm plateaus. This was not guesswork. It implies a sophisticated, practical understanding of geometry and landscape mechanics. Imagine a prehistoric surveyor standing at the quarry's edge. Their toolkit was observation and experience. They could visually assess a slope and know if it was too severe for their teams. They understood how different soils behaved when wet or dry. They could read the lay of the land, identifying natural causeways and predicting where a stone might gain dangerous momentum on a downhill run. This knowledge was a form of lived-in mathematics, a geometry of pragmatism passed down through generations of moving heavy things. The placement of the final monument itself often confirms this geometric intent. Many stone circles and alignments are positioned with specific astronomical orientations, requiring precise surveying over long distances. The same minds capable of aligning a monument to the solstice sunrise were certainly capable of plotting a manageable route for its components. This digital detective work bridges ancient intuition and modern computation. It suggests that before the first lever was ever placed, before the first rope was woven, a plan was etched not on parchment, but into the collective memory of the builders, a three-dimensional puzzle solved with feet, eyes, and an innate grasp of the Earth's own geometry. The rhythm of the work may have been its own form of prayer. When modern volunteers gather to move a replica stone, they often describe a shift that happens after the initial struggle. The individual efforts begin to synchronize. The separate pulls on the rope merge into a single, powerful pulse. A natural rhythm emerges, often accompanied by a shared chant or a steady beat tapped out on a log. This isn't just about making the work more pleasant. It reveals a hidden layer of ancient engineering. The coordination of dozens, sometimes hundreds, of individuals was the most critical component of the entire operation. A single person pulling out of sync could break the momentum, tangle the ropes, or even cause a dangerous snap. Ritualized movement and sound provided the solution. A lead caller, perhaps a spiritual figure or a seasoned foreman, would set the pace with a chant. Each syllable corresponded to a collective heave, turning chaotic muscle into a unified machine. The drumbeat served as a metronome for the entire site, its tempo dictating the lift of levers, the reset of rollers, and the steady drag of the ropes. From a purely practical standpoint, this ritualized coordination was essential. It prevented injury, maximized efficiency, and allowed the work to continue for hours under the sun. But to view it only as a management technique misses its deeper resonance. For the people involved, this rhythmic labor likely transformed a daunting physical task into a profound communal experience. The act of moving the stone together in sacred unison could have been as important as the stone's final destination. It wove the individual into the fabric of the community, each pull on the rope a stitch in a larger social tapestry. The journey of the megalith became a living ritual, a procession that physically manifested their shared beliefs across the landscape. The stone was not merely being transported, it was being conducted, accompanied by the voices and the focused intention of the people. This perspective helps answer the enduring question of motivation. The sheer scale of the effort makes little sense if the goal was merely a static monument. But if the process itself was a ceremony of unity, a reaffirmation of cosmic order, or an act of devotion to ancestors, then the labor becomes its own reward. The bluestone dragged from Wales to Salisbury Plain was not just building material, it was a pilgrim. The moai walked from the quarry was not just a statue, it was an ancestor joining the community. The backbreaking work was thus imbued with meaning, easing the burden not by reducing the weight, but by increasing the purpose. This intangible dimension is, by its nature, the hardest for science to excavate. No experiment can prove the content of a chant or measure the depth of a collective feeling. Yet its shadow falls across every successful reenactment, in the smiles of exhausted volunteers who have just moved the unmovable together. It reminds us that the greatest feats of ancient engineering were symphonies not just of physics, but of the human spirit. The chorus of voices that moved these stones was entirely human. Yet a persistent narrative insists the real architects came from beyond the stars, or belonged to a forgotten super-civilization wielding technology now lost to time. These are seductive stories, offering a clean, almost magical solution to a problem that clearly required immense effort. But the dusty, demanding work of experimental archaeology presents a powerful counter-argument, one built not on speculation, but on the tangible proof of ropes, wood, and mud. The evidence gathered from these modern trials demonstrates conclusively that the tools and the intelligence needed to build these wonders were already here, in the hands of the people who lived there. Consider the core claim of these alternative theories, that the methods used were so advanced they must have been beyond human capability at the time. The experiments directly dismantle this premise. Every successful movement of a multi-ton replica using Neolithic materials is a quiet but firm rebuttal. We have seen a stone walk with levers, glide on a lubricated sledge, and even be guided upright in a rhythmic march. None of these techniques require unknown physics or alien alloys. They require observation, patience, coordination, and a deep familiarity with local materials, all qualities abundantly present in ancient societies. The so-called mysteries of quarrying, transport, and placement are being solved not with tales of laser tools, but with demonstrations of stone mauls, wooden cribbing, and earthen ramps. The technology was not lost because it was never exotic to begin with. It was elegantly, brilliantly ordinary. This grounded understanding does not diminish the achievements, it elevates them. To attribute the pyramids or Stonehenge to extraterrestrials is, in a way, to rob our ancestors of their own genius. It replaces a story of profound human perseverance, social organization, and innovative problem-solving with a passive narrative of receiving gifts from a more advanced species. The real history is far more compelling. It is the story of a community surveying a landscape, calculating the path of least resistance, and then uniting for years, perhaps generations, to bring a shared vision to life. That is a testament to what people can accomplish together, a lesson in resilience and creativity that resonates deeply today. The alien theory offers a shortcut, but the human story offers a mirror, showing us a reflection of our own potential for collective greatness. Ultimately, the choice between these narratives is a choice about where we find wonder. Is awe only found in the fantastical and the unreachable, or can it be discovered in the gritty, determined reality of human effort? The experiments provide a clear answer. Watching a team of volunteers using nothing but ropes and logs inch a massive block forward is a deeply moving experience. It connects us across millennia to the sweat, the chants, and the triumphant moment when the stone finally settled into its intended place. That connection is real. It is forged in the shared language of physics and determination, a legacy written not by visitors from another world, but by the ingenious, earth-bound hands of our own human family. This evidence-based perspective does not close the book on mystery. It simply directs our wonder to the right source, the astonishing capabilities of the human mind and spirit when united by a common purpose. The calendar was as vital a tool as the lever. Our modern experiments often take place on dry, sunny days chosen for convenience, but the ancient builders had no such luxury. They worked within the rhythm of the seasons, and their true genius may have been in turning the weather itself into an ally. This temporal dimension forces us to ask, when was the work actually done? The answer transforms a static engineering puzzle into a dynamic dance with the environment. Imagine the difference between dragging a sledge across sun-baked, compacted earth and pulling that same sledge across a track slick with wet clay after the autumn rains. The effort required is not just different, it is exponentially less. Experimental teams have run these exact comparisons, measuring the pull force with strain gauges. On a dry, gritty surface, rollers can stick and grind, requiring constant adjustment and immense manpower. But on that same surface, lightly watered to mimic a dewy morning or a recent shower, the friction plummets. The wood glides, the ropes strain less, and progress becomes steady. This suggests that the most demanding transport phases might have been deliberately scheduled for the wetter months, when the very ground could be engineered into a natural lubricant. Conversely, consider the frozen north. In regions with cold winters, a completely different phenomenon emerges. Pouring water onto a prepared earthen ramp in freezing temperatures creates a surface of solid ice. A sledge on ice encounters almost negligible friction, a principle well documented in cultures that moved heavy logs over frozen ground. Could builders in temperate zones with frosts have used this to their advantage, moving stones in the crisp stillness of winter when the land itself became a slick, supportive highway? Seasonal planning extends beyond mere traction. It encompasses the entire logistical chain. Were the stones quarried in the dry season, when cracks in the rock were most visible and workable, then stockpiled near the quarry to await the wet season's transport window? Was the workforce likely drawn from an agricultural society, mobilized during the agricultural off-season, when hands were free from sowing and harvesting? This synchronization reveals a deep, embedded wisdom. It shows a society not fighting nature, but listening to it, folding their monumental ambitions into the existing cycles of the land and labor. The project timeline was not a straight line, but a series of pulses, of intense activity during optimal conditions followed by periods of preparation or waiting. This environmental intelligence may be the hardest evidence to dig up, for it leaves no physical trace in the archaeological record. Yet it is written in the success of the methods themselves, in the undeniable fact that these stones did move. They moved because their builders understood that the right day, in the right season, with the right ground underfoot, could make the impossible merely difficult and the difficult achievable. This was not just engineering, it was a profound collaboration with the world around them, a patient partnership with rain, frost, and earth that ultimately allowed them to rewrite their own horizon. The ache of wooden levers and the strain of hemp ropes now find their echo in the silent hum of a supercomputer. While hands-on experiments test the physical limits of materials, a new frontier of discovery has opened on the digital screen. Here, using advanced physics-based simulations, engineers can reconstruct ancient transport not with muscle, but with mathematics. They build virtual worlds where every variable can be controlled and every outcome measured with perfect precision. In these digital landscapes, a team of researchers can run not one, but thousands of transport scenarios in a single afternoon, a task that would take lifetimes to physically recreate. They adjust the slope of a virtual hill with a slider, change the consistency of the soil from dry pack to slick mud with a click, and increase the size of a pulling team from 10 people to 100 with a keystroke. Each simulation calculates the complex interplay of forces, friction, and human effort, revealing what might have been possible and, just as importantly, what likely was not. This computational power allows scientists to explore ideas too dangerous or prohibitively expensive to test at full scale. What happens to a 40-ton block on a steep incline if a primary rope fails? A physical experiment risks catastrophic damage and injury, but a simulation can model the failure safely, showing how ancient engineers might have designed redundancy into their systems. Or consider the challenge of navigating a narrow pass between two rock outcrops. A digital model can test multiple steering techniques using levers, showing which method offers the most control with the least risk of the stone becoming jammed. These virtual trials serve as a powerful filter, refining the myriad theories born from observation and physical experiment. They help identify the handful of most plausible, energy-efficient methods before a community of modern volunteers ever gathers to lift a single real log. It is a partnership between past and future, where silicon intuition guides the search for Stone Age solutions, ensuring that when we finally return to the mud and the rope, our efforts are directed by the clearest picture of ancient ingenuity we have ever possessed. This fusion of minds is where the past truly comes alive. The silent stones do not whisper their secrets to any one expert. They demand a conversation between disciplines. To solve a puzzle this ancient and complex, you need more than a single key. You need a whole ring of them, each held by a different kind of thinker. The archaeologist brings the map of human behavior, understanding the cultural landscape, the ritual significance of a site, and the social structures that could organize such labor. They ask why. The engineer brings the language of physics, calculating the pull force on a rope, the stress on a wooden lever, or the optimal angle for an earthen ramp. They ask how. The materials scientist brings a microscopic lens, analyzing residues on ancient rollers, the wear patterns on stone, or the tensile strength of reproduced plant fiber ropes. They ask with what. Alone, each perspective sees only a fragment. Together, they assemble a complete working model of the past. This interdisciplinary collaboration is the true engine of modern discovery, transforming speculation into testable science. A perfect example of this powerful synergy is the ongoing research surrounding the bluestones of Stonehenge. For decades, theories about their journey from Wales were just that, theories. Then, a team comprising archaeologists, geologists, and engineers decided to put them to the test. They didn't just read about sledges, they built them, using woodworking techniques from the period. They didn't just guess about routes, they used geological surveys to identify ancient riverbeds and terrain that would have been passable thousands of years ago. In one landmark experiment, they constructed a replica Neolithic monolith and attempted to transport it on a specially designed sled along a theorized route. The archaeologists ensured the materials and methods were period appropriate. The engineers instrumented the sled with strain gauges to measure the exact force required. The geologists advised on the ground conditions. The result was not just a successful stone movement, but a flood of hard data, the precise number of people needed, the effect of different lubricants, the points where the terrain became most challenging. This is the power of collaboration. It turns a historical mystery into a series of solvable engineering problems. It proves that the greatest monuments of antiquity were not built by isolated geniuses, but by communities of specialized knowledge, and today they are being understood the same way by communities of specialized researchers. The biggest breakthroughs happen not in the lonely archive or the solitary lab, but in the shared space where a soil sample meets a force calculation, where a flint tool's wear pattern confirms a physicist's model. It is here, at this vibrant intersection, that we are finally learning to listen to the full story the stones have been waiting to tell. The most profound lesson from these experiments isn't printed in a journal, it's felt in the trembling of a rope. Across the globe, a quiet revolution in public history is unfolding, not behind the glass of a museum case, but in the open air of archaeological parks and heritage sites. Here, the dusty trials of experimental archaeology are shared not just with fellow scientists, but with families, schoolchildren, and curious visitors. The goal shifts subtly from pure day to collection to creating a bridge of understanding, one that anyone can walk across. When a member of the public is invited to place their hands on a hemp rope and feel the immense tension of a stone beginning to move, history ceases to be a distant story. It becomes a sensation in the muscles, a shared breath with a team, a moment of collective triumph. This direct physical participation is transformative. It answers the question of how, not with a list of facts, but with the weight of experience. A child who has helped inch a wooden roller forward understands the concept of friction in a way no textbook can explain. An adult who has strained with a team to lift a lever grasps the sheer scale of the organizational challenge in their bones. These open-air demonstrations democratize the past, making the genius of ancient engineering accessible and deeply personal. They transform awe from a passive feeling into an active understanding. Sites like the Baalbek Museum in France or the Butzer Ancient Farm in England have made these live experiments a cornerstone of their educational mission. Visitors don't just see a finished dolmen, they witness the process of its creation, complete with the shouts of coordination, the scent of cut wood, and the palpable effort. This immersive approach does more than teach, it builds empathy. It fosters a profound appreciation for the ingenuity and perseverance of those who came before us, not as mythical supermen, but as resourceful people solving immense problems with the world around them. In this way, testing ancient methods becomes a celebration of shared human heritage. It connects us to a lineage of problem solvers and builders, reminding us that the drive to create, to collaborate, and to leave a mark on the world is a timeless part of the human story. The true value of moving a stone today is that it helps us understand and truly feel the magnitude of what was accomplished yesterday. Even with a stone successfully hauled to the site, the final act remained. The most delicate engineering challenge was not the long journey, but the last few feet. How do you take a multi-ton block lying on its side and stand it perfectly upright, or lift another to perch precisely atop it? This final emplacement is a frontier of its own, where the broad principles of leverage meet a need for millimeter-perfect control. Researchers are now designing experiments focused entirely on this climax of construction. One promising method revisits the lever and crib, but with a critical twist. By building a timber cage around the prone stone and using a sequential, opposing lever system, a team can literally walk the stone into a vertical position in tiny, controlled increments. Another theory involves a sophisticated use of earth and gravity, constructing a pit behind the stone's final location. The stone would be dragged to the pit's edge, then its base carefully nudged over. As the front end begins to tip into the pit, the stone's own weight and a system of guide ropes would pull it into an upright stance as it settles at the bottom. This method turns a dangerous lift into a controlled fall, a brilliant bit of physics theater. Testing these final placement techniques is a meticulous, high-stakes form of experimental archaeology, where a single miscalculation could mean a shattered replica and months of lost work. Yet each successful lift answers a fundamental question about the builder's confidence, their willingness to risk everything at the very last moment after years of effort. It reveals a mindset that saw the process through to an exacting, flawless conclusion. This precision leads to another enduring mystery, the quarry choice. Why would builders at Stonehenge source bluestones from mountains over 150 miles away, passing countless other rock outcrops? The experiments in transport efficiency make this choice even more puzzling. Current research is shifting from pure engineering to a blend of archaeology and geochemistry, analyzing the stones themselves for clues. Perhaps those specific quarries held a profound spiritual or ancestral significance, making the material itself sacred. The arduous journey may have been a required pilgrimage, a ritual of transformation that turned ordinary rock into a vessel of meaning. Or there might have been a very practical reason, a unique property of that particular stone, like its resonant sound when struck or its durability? The answer likely lies somewhere in between, a fusion of practical material science and deep cultural belief that we are only beginning to decipher. Looking ahead, the ultimate test looms, a grand, integrated experiment. The next frontier is not to test a single technique in isolation, but to combine the most promising methods into a coherent, start-to-finish operation. Imagine an ambitious project to move a newly quarried 20-ton block across a realistic kilometer of mixed terrain, using a period-appropriate toolkit, and then raise it onto a prepared platform. This would require a temporary community of researchers and volunteers, functioning like a Neolithic engineering corps for weeks or months. They would need to make real-time decisions, switch tactics when faced with an unexpected bog or slope, and solve the daily problems of feeding, sheltering, and organizing the workforce. Such an experiment would be less about proving a single point and more about experiencing the ancient process as a living system. It would teach us about the rhythm of the work, the points of greatest stress and failure, and the intangible social dynamics that turn a plan into a reality. The data would be invaluable, but the true revelation would be in the feeling, in understanding this work not as a series of solved equations, but as a sustained human endeavor filled with problem-solving, adaptation, and collective triumph. Each stone we move today brings us closer to the minds of those who moved mountains yesterday, not by giving us a simple answer, but by teaching us how to ask better questions. The true cost of a monument was measured in grain as much as in granite. Every person straining on a rope required a steady supply of food, a logistical reality that transforms our view of these societies from simple builders into sophisticated economic engines. The engineering experiments that define the number of laborers and the duration of their work provide a startlingly precise key to unlocking this deeper mystery. By calculating the human energy expended, historians can now model the immense agricultural surplus needed to sustain the project. A crew of 100 people working for a season might consume the equivalent of dozens of acres of harvested grain. This simple calculation shifts the entire discussion, for it reveals that the ability to move mountains was founded first on the ability to feed a non-farming workforce. The stones did not rise from a subsistence society, but from one capable of producing and managing a significant surplus. This economic foundation forces us to ask what kind of social structure could orchestrate such a sustained effort. Were these projects driven by powerful, centralized chiefdoms who commanded stored grain from vast storehouses, redistributing it to the laborers as a form of early wages? Or were they more communal, seasonal endeavors where the work coincided with agricultural downtime and was fueled by shared feasts and a collective commitment to a sacred goal? The physical experiments with sledges and levers thus provide a surprising key to understanding social complexity. The engineering is the visible tip of a vast, submerged iceberg of organization. To plan a harvest that could feed hundreds of extra mouths for months, to manage the storage and distribution of that food, to coordinate the labor cycles of farming and construction, all of this speaks to a level of economic planning and social cohesion that rivals the engineering feat itself. The monument is not just an expression of belief, but a receipt for a society's economic health and managerial skill. It tells us that these communities were not merely surviving, they were thriving, with enough stability and foresight to invest their collective energy in a legacy that would outlast the seasons. This perspective completes the picture, showing that the silent stones stand not only as testaments to physical ingenuity, but as enduring markers of a society's profound ability to organize, to plan, and to dream together across generations. A global tapestry of experiments now lets us compare notes across continents. In Japan, teams have recreated the construction of massive keyhole-shaped tombs known as coffin, using earthen ramps and large workforces to move the stones and soil. Along the windswept coast of Brittany in France, researchers have tested methods for moving the thousands of standing stones at Karnak, focusing on the use of oxen and wooden sledges across the region's unique terrain. And in the dense jungles of ancient Mexico, theories about transporting the colossal Olmec head, some weighing 20 tons, center on the use of rafts along river networks and rollers across prepared causeways. When we place these experiments side by side, a fascinating pattern emerges. From Japan to France to Mexico, we see the recurring use of fundamental tools: the lever, the roller, the sledge, and the ramp. This is not a coincidence. It is a testament to the universal laws of physics. Gravity, friction, and leverage behave the same way in every corner of the world. Faced with the same basic problem of moving immense weight, human minds, separated by oceans and millennia, arrived at similar mechanical solutions because the physics itself dictated the most efficient pathways. The roller was not a secret passed between cultures. It was an inevitable discovery for anyone trying to reduce grinding resistance. Yet woven into this universal framework are threads of brilliant local adaptation. The proposed upright walking of the Easter Island moe stands out as a strikingly unique method, one that seems born from the specific form of the statues and the island's own resource limitations. In the forests of northern Europe, experiments often highlight the use of abundant timber for elaborate wooden trackways. In contrast, in the steeper, rockier landscapes of the Andes, research points more toward ingenious levering and stone-on-stone pivoting techniques that required less wood. These divergences speak to a different kind of intelligence, a cultural ingenuity shaped by environment. What materials were at hand? Was there abundant strong timber, or was wood scarce? Was the terrain flat, swampy, or mountainous? Was there a large population to mobilize, or a smaller, tightly knit community? The solutions evolved to fit these local conditions. The universal principles provided the grammar, but each culture wrote its own sentence, its own story in stone, using the vocabulary of its own landscape. This comparative view does more than solve puzzles. It reframes our understanding of human innovation. It shows that our shared genius lies not in possessing a single, secret blueprint, but in our universal capacity to observe, experiment, and adapt. We see a common human mind at work, yet one that expresses itself in wonderfully diverse ways. Each monument a unique answer to the same eternal question: how do we make our mark upon the earth? The rope in your hand connects you to more than just a stone. It ties you to a living landscape, a cultural legacy, and a set of profound responsibilities. As experimental archaeology grows more ambitious, its practitioners face a critical balancing act, one that extends far beyond the physics of friction. Every decision to cut a mature oak for a sledge, to quarry a new stone block, or to alter a patch of land for a test track carries an ethical weight. How do we learn from the past without harming the future? The field has evolved a thoughtful framework to guide this work, built on principles of minimal impact and maximum respect. Before a single tree is felled, researchers now conduct thorough environmental assessments. They source timber from sustainable forestry projects or use trees already slated for removal due to safety or land management. Replica stones are often cast from concrete rather than freshly quarried from ancient, sensitive sites. The goal is to leave the lightest possible footprint, ensuring that the quest to understand ancient engineering does not itself become an act of thoughtless consumption. This mindful approach extends to the historical accuracy of the reconstructions themselves. A responsible experiment is transparent about its limits. It clearly distinguishes between methods that are strongly supported by archaeological evidence, like the use of sledges and rollers, and those that are more speculative but mechanically plausible, like the upright walking of moe. The most valuable projects are those that test a specific, evidence-based hypothesis, not just an appealing idea. They document every failure as carefully as every success, because a technique that does not work is just as informative as one that does. This rigor ensures that the knowledge gained is a genuine contribution to our understanding, not merely a compelling spectacle, but perhaps the most vital ethical dimension lies in the human connection. These are not anonymous ruins, they are the cultural heritage of living peoples. For the descendants of the megalith builders, from the Rapa Nui of Easter Island to the indigenous communities of the Americas, these stones are active parts of their identity and history. The most progressive research now actively seeks collaboration with these communities from the very beginning. This means moving beyond simply asking for permission to inviting genuine partnership. Elders and knowledge keepers are consulted not as a formality but as essential guides. Their oral histories, traditional stories, and cultural perspectives can offer clues that pure engineering might overlook, shaping the very questions being asked. This collaborative model transforms the work. It shifts from an external investigation of a mystery to a shared exploration of a legacy. It acknowledges that the deepest understanding comes from weaving together scientific data with living memory. This respectful engagement helps prevent the appropriation or misinterpretation of sacred traditions, ensuring that the narrative told about these monuments includes the voices of those for whom they hold the deepest meaning. Ultimately, these ethical considerations are not obstacles to discovery, they are its necessary foundation. They remind us that the stones we strive to move are more than inert objects of study. They are anchors in a continuous human story. By approaching them with care for the environment, rigor in our methods, and respect for their living descendants, we honor the full depth of that story. We ensure that the light we shine on the past illuminates with wisdom, not just with the glare of curiosity, building a bridge of understanding that is as sturdy and enduring as the monuments themselves. The evidence points not to a lost secret, but to a well-stocked workshop. If we could peer into the mind of a Neolithic master builder, we would not find a single magical blueprint. Instead, we would see a mental inventory, a versatile and practical toolkit assembled from the world around them. This was not a collection of gadgets, but a profound understanding of principles. The physical components were straightforward. A sturdy wooden sledge shaped from a single massive oak trunk to distribute weight, a bundle of strong, straight-grained ash poles for levers and rollers, great coils of rope thick as a man's wrist, painstakingly twisted from plant fibers or strips of hide, and perhaps a trough of simple lubricant, a slurry of wet clay or animal fat to transform grinding friction into a slick glide. These were the tangible tools, each one born from an intimate knowledge of local forests, plants, and soils. Yet the most critical items in this toolkit were intangible. The first was a deep, experiential map of the terrain, an ability to read a hillside and know if it could be traversed, to identify the firmest ground, and to foresee where a stone might gain dangerous momentum. The second was a masterful grasp of group dynamics, the rhythmic coordination that could turn 100 individual pulls into one unified force. This synthesis of physical and social engineering reveals the true nature of the achievement. The builders possessed a repertoire of techniques, not a single trick. On a long, flat stretch, the sledge and roller method would make steady progress. At a steep embankment, the team would switch to levers and cribbing, walking the stone up inch by inch. Faced with a patch of soft ground, they might lay down a temporary track of wooden rails. Their genius was adaptive intelligence, the ability to diagnose each new challenge the landscape presented and select the right tool from their collective knowledge. This flexible, problem-solving mindset demystifies the monuments. It shows that moving mountains was not an act of supernatural power, but the result of observation, experimentation, and relentless perseverance. It was a marathon of practical physics, run one coordinated step at a time. The stones did not move because our ancestors knew something we have forgotten. They moved because they understood, with brilliant clarity, the very world they walked upon. The stones have finally settled, and in their silence we hear a different story. The engineering experiments we have walked through together do far more than solve a technical puzzle. They perform a profound act of restoration. They return agency and brilliance to the very hands that shaped our world. By gripping those replica ropes, by feeling the strain of a wooden lever, we bridge a gap of thousands of years, not with speculation, but with shared sensation. We understand in our muscles and our minds that these monuments rose not from magic or visitors from the stars, but from the most powerful forces on Earth: human creativity, cooperation, and relentless determination. Each muddy trial, each calculated simulation, peels away the myth to reveal a far more inspiring truth. Our ancestors looked at a mountain and saw not an obstacle, but a material. They faced an impossible distance and plotted a path through patience and physics. They transformed their very landscape into a toolkit and their community into an engine. The true revelation of these experiments, then, is not really about stones at all. It is about us, about our enduring human capacity to look at a seemingly insurmountable challenge and say, together we can move this. That legacy is written across the globe, in every circle, every standing stone, every colossal head gazing toward the horizon. They are permanent reminders that the greatest structures we build are not made of granite, but of collective will. If this journey into ancient ingenuity resonated with you, please like this video and subscribe for more explorations into the mysteries of our past. We would love to hear your thoughts. Which experiment or method did you find most convincing? Share your perspective in the comments below.